Every movement you make, every thought you have, every heartbeat, blink, and breath begins with something you can't see. Not a muscle, not a bone, but a tiny electrical signal racing through your nervous system at incredible speed. It is the transmission of traits along a neuron's length that allows for information to be received, analyzed, and responded to. This is what is known as an action potential.
This section of the nervous system focuses on how neurons communicate using electrical signals called nerve impulses. A nerve impulse is not electricity in the way a wire conducts current, but rather a controlled movement of ions across a cell membrane. The neuron structure, particularly the axon, allows this signal to move rapidly over long distances. Everything we're about to discuss builds toward understanding how these impulses begin, travel, and are transmitted to the next cell. At rest, a neuron is not inactive. It is electrically charged. This state is called the resting membrane potential, typically around -70 millivolts. The inside of the neuron is more negatively charged than the outside, largely because of large, negatively charged proteins trapped inside the cell and an unequal distribution of sodium and potassium ions. This separation of charge stores potential energy. Think of it like a stretched rubber band. No movement yet, but energy is ready to be released. The process of establishing this charge difference is called polarization, and it is essential because without it, a neuron cannot fire an impulse. The resting membrane potential is actively maintained by the sodium-potassium pump, a protein embedded in the neuron's membrane. This pump uses ATP, which means energy is required just to keep the neuron ready to fire. For every cycle, the pump moves 3 sodium ions out of the cell and 2 potassium ions in. Because more positive charge leaves than enters, the outside of the cell becomes relatively more positive. This constant ion movement prevents charge equilibrium and maintains the neuron's readiness to respond to a stimulus. An action potential begins at the nodes of Ranvier, which are gaps in the myelin sheath. This is illustrated in the diagram, sodium channels OPN causing a voltage change. When a stimulus causes the membrane potential to rise above -70 millivolts and reach the threshold of -55 millivolts, voltage-gated sodium channels open. Sodium ions rush into the cell due to both concentration and electrical gradients. This rapid influx causes depolarization, and the membrane potential can rise as high as +35 millivolts, as shown in the diagram. This is an all-or-nothing event. If threshold is reached, the action potential will occur fully. Almost immediately after depolarization, sodium channels close and potassium channels open. Potassium ions flow out of the neuron, restoring the negative charge inside the cell, a process called repolarization. However, potassium channels close slowly, causing the membrane potential to dip below the resting level. This is known as hyperpolarization, where the neuron temporarily becomes more negative than -70 millivolts. During this time, the neuron is in a refractory period and cannot fire another action potential, ensuring signals move in only one direction. This graph summarizes the entire action potential over time. The horizontal axis represents time in milliseconds, and the vertical axis shows membrane potential in millivolts. Starting at resting potential, the curve rises sharply once threshold is reached. This is depolarization caused by sodium influx. The peak represents maximum depolarization. The downward slope shows repolarization as potassium exits the cell, followed by a brief hyperpolarization before returning to rest. This entire process happens incredibly fast, often in less than 5 milliseconds, allowing rapid communication within the nervous system. This diagram highlights the importance of myelin. When the myelin sheath is intact, action potentials regenerate efficiently at each node. In multiple sclerosis, the myelin sheath deteriorates. Without insulation, impulses slow down or fail entirely. This explains symptoms such as muscle weakness, poor coordination, and slowed reflexes. The disease illustrates how critical myelin is for proper nervous system function. When an action potential reaches the end of a neuron, it cannot jump directly to the next cell. Instead, the signal crosses a tiny gap called a synapse using chemical messengers called neurotransmitters. These neurotransmitters are released into the synaptic cleft and bind to receptors on the next cell. Depending on the neurotransmitter, the signal can be excitatory, opening ion channels and triggering a new action potential, or inhibitory, preventing the next neuron from firing. This chemical step allows precise control over nervous system signaling. When an action potential reaches the end of a neuron, it cannot jump directly to the next cell. Instead, the signal crosses a tiny gap called a synapse using chemical messengers called neurotransmitters. These neurotransmitters are released into the synaptic cleft and bind to receptors on the next cell. Depending on the neurotransmitter, the signal can be excitatory, opening ion channels and triggering a new action potential, or inhibitory, preventing the next neuron from firing. This chemical step allows precise control over nervous system signaling. When an action potential reaches the end of a neuron, it cannot jump directly to the next cell. Instead, the signal crosses a tiny gap called a synapse using chemical messengers called neurotransmitters. These neurotransmitters are released into the synaptic cleft and bind to receptors on the next cell. Depending on the neurotransmitter, the signal can be excitatory, opening ion channels and triggering a new action potential, or inhibitory, preventing the next neuron from firing. This chemical step allows precise control over nervous system signaling